Thank you very much, Jim. I'm very delighted to get this invitation to give a talk here today. And as Jim mentioned, I'm going to talk about observations, so-called real observations. Here we go. I hope you can see it's changing now.
Yep.
Okay, so you could ask from the onset, why are we so interested in climate and climate change just now? And one reason is probably many headlines in newspapers, like this one, describing a very sad situation in Germany 1.5 years ago, with a serious flooding after a rainstorm, where a valley with houses, as you can see in this picture here, was flooded. And many people are asking themselves, or we are being told, that we are just now living in a climate crisis. It depends, of course, on your background. And if you take a look on this picture here, which shows the valley with buildings in a non-flooded and flooded situation, you will probably notice that all the houses are located on a flat valley bottom. That's a so-called river plain, because that's an easy place to build buildings. But if you build buildings or settle down on a river plain, you have to expect that from time to time you will get flooded. If there was no recurrent flooding here, there would be no river plain. So it's not completely unusual, although it's very sad for the people involved. Here's what I'm going to talk about. I will talk a little about atmospheric temperature, ocean temperature, sea level, sea ice, snow, wind and storms, and then come back to talking a little about the importance of oceans. And finally, I'll try to draw a few conclusions. So let's start off with our atmospheric temperature, because many people who are involved in this climate debate, they are talking about air temperatures. And if you take one database where you can get satellite observations of near surface temperatures and compare the average for last year, 2021, the last full year, and compare them with the average of the previous 10 years, you see that last year, or 2021, was not a particularly warm year. Actually, the blue color, which tend to indicate lower than average temperature, and the warm colors indicate warmer than average temperature. The blue colors are dominating here. And also, if you take a different look like this, where you take the mean annual air temperature as recorded by satellite, mean annual air temperature is what is indicated here, year by year from 1979 until the last full year, 2021, you see that this year was not especially warm, but we are just now in a warm period, no doubt about that. Also, if you take a look on a much longer time series, these satellite series are not longer than some 40 years, almost 45 years. Here's an English database, the Hadcrut series, which goes back to 1850 here on the time scale. And here we are up at 2021. Here the horizontal line is simply the average for 30 years between 79 to 2008. But also here you see we are in a warm period, but last year was not especially warm. You can also say that this is final part of the so-called Little Ice Age. Then we had a warm period around the Second World War, a cool period into the 60s and the 70s, and then warming after that. However, if you go to the original data, here is one satellite series. You normally will get them with a monthly resolution. And then, of course, you had a lot of ups and downs. And in order to convey a picture of the overall development, I've calculated this curve here, which is a simple average for between 37 months. This is roughly 3 years. But here you see a lot of peaks, El Niño, some also a graphic feature in the Pacific, another one here, and so on. And you see the so-called period, 15 years without temperature rise, the so-called pause here. And now we're up on a higher level, and temperatures, we have to wait to see what they are going to do in the future. And if you, this was satellite temperatures in the lower troposphere, which means it's indicating the temperature, well, let's say 1-2 kilometers above the surface. But if you take traditional surface observations, the look may be like this. Once again, the British Hadcroft series. And it looks pretty much like the satellite series, although the temperature increase is somewhat bigger. The so-called pause here, 15 years without anything or not very much happening, is indicated here with a slight temperature increase. But the main features, you can recognize them between these observations and the satellite observations. Here's another surface series, American, the GIS series. And once again, you will recognize what you saw on the previous slides. But here I've also indicated the version which was published in May 2015 with a red curve here. And you can see this series here indicated a pause until May 2015. Then there was a change, a new version of the data series, and suddenly there was no pause anymore, but now it's creep towards higher temperatures. And this is a feature which you see in almost all of these temperature series, that values are changing. So if you ask one series, what was global temperature in February 1991, you get one answer. And if you ask the same question half a year later, you'll get a slightly different answer. So historical data are slowly being changed for different reasons. Some are probably clear, but others are less clear, at least to me. Oh, we have to go the other way. In order to illustrate this ongoing change of historical data, which I don't believe many people are aware is happening. I noticed this first time in May 2008, and since then I have taken a copy of all data series each month. So I can actually compare for this series here, the GIS series, the May 2008 version with the November 2022 version. And subtract one from the other, and you'll see that the net result is that the early part of the record is dominated by, you could call it administrative warming. And then the period between the turn of the century until the Second World War is dominated by cooling values. And then in the final part of the diagram, since the 70s, warming is once again dominant. So a lot of things is happening. And you can see the warming here is up to 0.1 degree. The cooling here is about 0.1 centigrade. So the net change is about 0.2 centigrade. And that's quite significant, actually. In order to illustrate this development in another way, you can take a look at January 1910 and January 2000 in the next slide. Here we are in April 2008, and here we are up to October 2022. And this is the historical record of the reported temperature for January 2000 since 2008. Slowly getting higher and higher, and similar for January 1910, slowly getting lower and lower. Sometimes pretty marked changes. But if you in May 2008 ask what was the warming between 2008 and 2000 and 1910, the answer would be 0.45 centigrades. And if you come up with the same question today, the change is now increased to 0.66 degrees centigrade. Quite a significant change. Ocean temperature, very important, and I will talk a little about the Argo profiling floats. It's a fascinating program where a lot of floats is distributed in almost all of the oceans. So today we have about 3,800 free drifting floats, and they operate in this way, as you can see on this diagram, spend some time on the surface, communicating with the rest of the world. Then it's descending within 6 hours to about 1,000 meters below the surface, drifting in this depth for 9 days, and then it goes down to about almost 2,000 meters below the surface, and then it comes up again. And all the time it records temperature, salinity, and so on. And then it resurfaces and transmit data back via satellite. So this is an enormous database which have developed from these data, and very interesting. And I've not been able to find any updates which goes beyond August 2020, probably because it's an enormous job to actually update this database. But I'm showing some of the main results in this diagram, which starts in 2004. And here to the right, we are 2021. This diagram here, excuse for the numbers, which are probably too small to be seen, but you can see in the beginning, this is oceans around the equator, 30 degrees north to 30 degrees south. And around 2012, you see a temperature increase, and then it looks as if we are reaching a maximum here. If you do the same exercise for all measurements from the surface down to 1,900 meters below the surface, for the Arctic oceans between 55 and 65 degrees north, you see not a very interesting development in the beginning, but then things are cooling down. So as oceans around the equator has been warming the last 10 years, the oceans around the Arctic has actually been cooling. Near the Antarctic in the southern hemisphere, not very much has been happening, a slight warming, but not any dramatic development. And if you on the lowermost panel take the average for all the global oceans, of course it's the oceans around the equator which are dominating, because you have between 30 degrees north and 30 degrees south, you have 50% of the global surface. Then you see this increase of temperature since 2012. Here's a diagram, also very small numbers, but it shows from 2004 until 2021, the average temperature change near the surface, 2.5 meters below the surface. And then you have different intervals, and here we have the temperature change at 1,900 meters depth. What is interesting is you can see there's an annual cycle, no big surprise. And you can actually trace this annual variations down to 100, 200 meters below the surface. You could see that this peak here is coming here with some delay at 100 meters depth. But what is interesting, and I'm not looking into the details of this, but to me it looks as if we have some kind of temperature increase here at 1900 meters depth, and you can trace it coming up towards lower and lower depth. And apparently it takes a couple of years, but this diagram indicates to me that the temperatures in the ocean, or in the uppermost 1900 meters, the ocean is of course partly controlled by what is happening near the surface, but there may also be some contribution of the dynamic coming from greater depths actually, which would not be a very big surprise, but it's interesting to see. If you take all the data from these about 15 years, and here we'll put them on a scale from the surface, 0 depth, to 1900 meter, and ask what has been the total change of temperatures over these 15 years, you see we have a pretty significant temperature rise, somewhere between 0.25 and 0.3 degrees near the surface. But below 300-400 meters, the temperature increase has been very small actually. This is for all the oceans. But if you subdivide it once again into oceans near the equator, oceans near the North Pole, and oceans around the Antarctic, you see a big difference. Here we have equator warming near the surface and not any significant change with depths. Near the Antarctic, some warming near the surface and small change with depths. But the northern oceans really stand out here. A lot of cooling going on in this time interval, 15 years. Only below about 1400 meters depth, you see slight warming. So there's a lot of interesting dynamics going on in the oceans, which are indicated by this still short data series, only about 15 years. But this is a very interesting data series from my point of view. You see the globe with the annual mean net surface solar radiation in watts per square meters indicated. And you see near the equator, we have the maximum insolation. Near the equator, there's an area with lower insolation. This is because of rising air masses. You tend to have a cloud cover here all the time. Here we have made two sections north-south, one in the Pacific here, and one in the Atlantic Ocean here, which shows some interesting contrasts. But we have to bear in mind that these are two-dimensional diagrams, and so it's only a simplistic way of looking upon things, but it's interesting nevertheless. Here's a Pacific profile. Here we are near the South Pole. Here are equator. Here we are near the North Pole. Here we are at the surface, and here we're down at 1900 meters depth. And the colors indicate the total net change over these 15 years. And you see most changes are taking place near the surface, and the general information here is that warming in the northern part of the Pacific. Not very much going on at depth, a little cooling near the South Pole. Then if you do the same for the Atlantic Ocean from near the Antarctic all the way up to the neighborhood of Iceland, it looks like this, the development over then net development over these about 15 years. Here we are near the South Pole, up here we are near Iceland. A little warming near the equator, south of the equator, but below the surface layer some cooling. But the most significant is actually this cooling, once again, we see in the northern part of the North Atlantic. This is rather fascinating because we all know that the Arctic sea ice has been decreasing in extension, but nevertheless we see cooling here. But that's what the data are telling us. So for that reason, I took a more detailed look using this database on a profile following 59 degrees north here from the longitude of Greenwich until 30 degrees west, because here we have a section across all the warm water which comes into the Norwegian Sea, and the North Atlantic Current, or the Gulf Stream, as everybody knows, is extremely important for people living in Europe, especially northwestern Europe. So this is what we see on this diagram here. Here we are at the surface back 2004, and then time goes on, ending here 2020. And here we are at the surface, and here we're down at 800 meters depth. And you clearly see the summer warming near the surface and winter cooling. But what comes out here is, especially 2016, this is a very interesting year. There was a lot of cold water extending almost to the surface here. And if you take all these numbers and put them into a simple graph, it looks like this. So here we have the time scale, and here we have a temperature scale, and you can see cooling going on, reaching a minimum around 2016, and then some indication of a recovery after that. So there's a lot of dynamics going on here. This is a cross-section across what you probably could say is the North Atlantic current or the Gulf Stream. Of course, this could have influence for what will happen in the Arctic for the coming years. Sea level, another thing which is very interesting, and the latest fiscal report from the IPCC published last year indicate this diagram here, among other diagrams, where in this diagram you have the historical record here. Here's a sea level rise. And here we have the time going on. And you can see if you move forward, of course, to these predictions here, to the turn of the century in about 75, 80 years, most of these predictions come out with a sea level rise, global sea level rise, somewhere between 0.5 and 1 meter. Now, if you look into the data, you can look into satellite data, or you could look into data which are measured along the coast. But I will start with the satellite data, which are published by the University of Colorado. And here we have a time scale, 1992, and here we are up to today. And you see the individual monthly observations here. And you see we are talking about you can make several trend lines here, and depending on the time interval, they will be somewhere between 3 or 4 millimeters of sea level rise per year. So that would give, if you extrapolated that to the turn of the century, about 30 centimeters of sea level rise globally. Now, I myself living near the coast, so I'm more interested in what is actually measured near the coast by sea level gauges, which is a much more simple observation to do than observing sea level change from a satellite. And but the tricky part is you need to find a place which from a geological point is stable, not exposed to land rise or land sink, but is stable. And in Denmark, you have such a locality, which apparently has been geologically stable, no uplift, no the opposite for more than 1,000 years. And there's a very long record from 1897 of monthly observations of sea level here, all the way up to almost to today. And it's relatively stable. And you can see that here we're talking about relative sea level rise in relation to land, about 0.8 millimeters per year. So that's much smaller than what is recorded by satellites. But if you're living at the coast, I would put my money on this kind of measurement compared to the satellite measurement, personally speaking. Oslo, which is another place where I'm living or have been living, was covered by several kilometers of the ice during the last glaciation and still exposed to land right after that. So you can see on the sea level curve from Oslo, which goes back to 1914, that sea level is going down in relation to land. So land come out of the ocean with a velocity of almost 4 millimeters per year in Oslo. But now when they published the latest IPCC report last year, they also published a lot of sea level calculations for the future. And if you plotted this for Oslo, it looks like this. So according to the IPCC, the ongoing sea level drop in Oslo just around 2020 is supposed to go into a sea level increase. Doesn't look so convincing to me, but of course we will have to wait and see who is correct here. Sea ice, also a very interesting point, also addressed by the IPCC, and they have this diagram showing the September. Sorry, I have to go back. Here we are. September sea ice extension and how it should develop in the future. And if you plot the latest September 2022, you can see it is not exactly in the spaghetti here. It's already outside, pretty much. If you plot satellite observations of the sea ice since 2005, looks like this, a lot of ups and downs. And during the last few years, you actually see sea level or increase in the extension of the Arctic sea ice. You can also compare it with the Antarctic sea ice. In this diagram, I've plotted since about 1980 the development of the sea ice in the Arctic, and you see the decrease of the extension here. The last few years, an increase. And if you do the same for the Antarctic ice, you see the opposite development. But once again, 2016, something happens, a sudden decrease, and then perhaps a slight recovery again. And in the lower part here, you see the global extension of sea ice here. A drop 2016, and then a small coming back here. Snow is supposed to be a thing of the past. There's been a lot of newspapers, headlines about that. Snowfalls are just now a thing of the past. But if you look into the observations, you can see something else is happening. But the IPCC report indicate for the spring season, March, April, May, ongoing decline, which according to different forecasts is supposed to go on. But if you plot the satellite-based snow cover extension with a weekly resolution since 2000, you see it's actually a very stable system. Small ups and downs, but no dramatic development. And also, if you take the entire data series going back to 1972, it's the same picture. Maximum goes up and down a little from year to year. The minimum is more stable, but overall there's no dramatic development. The snow cover in the northern hemisphere, to me, it looks as if it's a pretty stable system actually. Also, if you plot the snow cover in this way here, for the winter season, the spring season, the summer season, and the fall season, you see a stable situation for the winter. From a statistical point, a small decrease for the spring season, same for the summer season, and for the fall season, from a statistical point of view, a small increase actually. So it's not a system which seems to be breaking down at the moment. A few words about winds and storms. You can calculate what is called the accumulated cyclonic energy, which gives some expression about the destructive power or storms in the Atlantic basin. And you have data, so you can do that since 1850. So here's a peak around here, another peak around shortly after the Second World War, and a peak shortly after the turn of the century. And if you do a 4-year analysis on this, you see there are several periods, but one period which is very clear and significant is about 60 years, which is a period which you know from many data series actually. Also, if you plot a diagram for the number of hurricanes which have landfalled in the United States, you can see similar development, but the main point is that there's no dramatic increase taking place during the last decades. If anything, there's actually a small decrease, but it looks as if it's a rather stable system, but with big interannual variations, of course. And when we're talking about storms and damage of storms, this diagram here shows the global values on a time scale from 1970 to 2020. Here we have from the northern hemisphere, here we have for the southern hemisphere, and you can see the global signal is mainly derived from the northern hemisphere, probably because we have a much more uniform hemisphere in the southern hemisphere compared to what we have in the northern hemisphere, where we have all the major land areas. And just to give an idea about some of this is also indicated by point measurement. So I found wind data from a Norwegian lighthouse in South Norway, sitting very exposed, almost out in the North Atlantic, where you have data back from 1930. There's a break during the Second World War, but all the way up to today. What you see in the lower panel is the average wind speed, and what you see in the upper panel is the gust, the maximum wind speed. And you can see the average wind speed is almost unchanged. There are small variations, but no big increase here. And actually, in the late 40s, we have a peak in the gust wind speed, the maximum wind speed, which is not surpassed today. So it looks as if it's just natural variations which are causing these changes here. There's no uniform or linear development, at least. Finally, I would like to show you a couple of diagrams which I made because when you're sitting and looking at all these numbers, you get some ideas. Some may be good, some might be less good. I would say often nature provides us with remarkable simple answers to big questions if we ask the correct questions. And one example is that, in my opinion, nature, in a very simple way, actually shows us what is important for the global climate and what should be looked into if you want to understand the global climate. Coming back to the ocean observations, here we have a time series from 2004 to 2015, showing near the surface. You see the annual cycle here, and then you can trace this summer peak here all the way down to 100 meters, and actually from a statistical point of view, you can trace it down to 200 meter steps. But you can see it comes with a delay, so clearly it's a signal which initiates at the surface and then is transmitted towards greater depth. And if you do a correlation analysis between the surface temperature and the temperature at 200 meter steps, you find that the delay is about 20 months at 200 meter steps. Now you can make a diagram like this. This is showing our planet. Up here, we have the atmosphere. Here we have the sea surface. Here we have the oceans, and here we have the continents. The sea, the oceans takes up more than 70% of the surface area. And now we saw that if you take the sea surface temperature, then we can trace it takes about 20 months before the signal in a weak form is observed at 200 meter steps. And if you do the same with the standard global surface temperature, you find that if you know the sea surface temperature, then you know something about the global average surface temperature 0.4 months later, also with a delay. And if you compare it with the satellite observations in the lower troposphere, sea surface temperature comes first, and then after 2 months, you can observe the temperature signal by the satellites. And if you only focus on land surface temperatures, the delay from the sea surface to land is also 2 months. What is significant here, from my point of view, is that the sea surface temperature is a leading temperature. So the global temperature signal, no matter what you're looking at, ocean or atmosphere or land, it comes from the sea surface. And that's interesting because according to the carbon dioxide hypothesis, the main development should happen in the upper troposphere, 8-9 kilometers above the surface, and then the signal should later be seen at the surface. But here we have the delay in the completely opposite direction. So the theoretical effect of increasing CO2 is apparently drowning in these natural systems here. So I would say the big question to me is actually what controls the sea surface temperature. If you know what controls the sea surface temperature, you know in a simple way what controls the global climate. So that would be my take-home message. What controls the ocean surface temperature controls the global climate. And some candidates in my head would be, of course, the sun and modulated with a cloud cover. But it's something which should really be looked into. So if I have to come up with a couple of conclusions and one suggestion for important future research focus, I would say these are the conclusions. All the data series do not support the notion of standing in a climate crisis. It looks very natural to me, at least. I see no clear influence of carbon dioxide. Another thing is that ocean surface temperature apparently controls the global climate. The signal comes from the ocean surface. And for that reason, I would suggest that scientists should really focus on understanding all the details in what are controlling this ocean surface temperature. I could point to the sun, the cloud cover, the amount of sediment or organic life in the ocean, and the wind action. There will be a lot of factors probably, but in my head I would say that the sun and the cloud cover is among the main factors. But this is really something somebody should look into the details. So this is what I would like to say this evening. Thank you very much for your invitation so far.